Imagine sitting on the shore of a massive lake covering the Missoula Valley and stretching 3,000 square miles in every direction. The water, enough to fill two Great Lakes, floods all but the tops of the tallest mountains in the western part of what is now Montana. Imagine a dam 7 Statues of Liberty tall, made of crystalline blue ice. The dam fails, and the lake is gone in just a matter of days. This is the story of Glacial Lake Missoula and the catastrophic events shaping our landscape thousands of years ago. The echoes of those events can be heard today in the stories the rocks in the river tell those who are curious and who listen closely. This scene 18,000 years ago began when Glacial Lake Missoula was formed by a lobe of the Cordilleran ice sheet, 2,000 feet high and 30 miles long. The glacier, located at the Purcell Trench, a large valley at Sandpoint, Idaho, blocked the path of the Clark Fork River. As the water rose to the depth of 2,000 feet behind the giant dam, the lake embraced the flooded mountains with fjord-like arms. Those arms included the Bitterroot Valley to the south, the Flathead Valley to the north, and an eastern arm as far as Deer Lodge. The massive ice structure strained under the pressure of the backed-up water for a long time. The lake bed, composed of gravel and sediment, compressed under pressure. Quiet waters lapped on the beaches of the extensive and intricate coastline, and mountaintops peaked above the water's surface.
When we walk around Montana and we see the rocks around us, a geologist's job is to be very observant and pay attention to those rocks and learn to tell the story of the history of the landscape. And the history of Lake Missoula is a great example, piecing together these different pieces of evidence, these different rocks and landscape forms that individually didn't make a lot of sense until we put them all together, and then we learned this really amazing story.
The ice fields built slowly over the course of 200,000 years. The Purcell lobe formed the dam, backing up the river's water behind it. As the climate warmed toward the end of the Ice Age, the ice began to melt. What had taken 200,000 years to build took a mere 2,000 years to vanish. The rising water and melting ice reached a critical breaking point. Dripping, slippery ice chunks released their hold from the massive glacier where the dam met the mountain. Calved icebergs floated on the lake. The front of the gigantic ice chunks bobbed in the water, pushed by howling winds and waves. The calving action triggered extensive sloughing, known as rotational failure, which chewed into the spine of the ice dam. This action was so powerful that the enormous dam broke, releasing a torrent of water. Glacial Lake Missoula was gone.
So there's no question, using this rotational mechanism, that we could have started on the Montana side and eaten clear through the core of the dam and gone out the Idaho side. Once you get started downhill on the Idaho side, the dam it's gone, because now you're working downhill on ever thinner, weaker ice.
The calving of other glacial lobes in the lake launched thousands of icebergs in a navy that sailed the rushing river and piled up in narrow canyons. The grinding ice left echoes on the landscape at Rainbow Lake, Eddy Narrows, and other locations along the river's course. The rushing water tore through northern Idaho, eastern Washington, the Columbia River Gorge, Oregon's Willamette Valley, and finally released its fury into the Pacific Ocean at Astoria. Imagine this cataclysmic event draining the entire ancient lake in not years, not months, but only a few days. Torrents of water destroying everything in its path. The sound must have been deafening. At once, the waters receded and the dripping canyons were silent. Total devastation. Scoured land, cleaned of all organic matter, scarred with ripples frozen in time and drainages instantaneously reshaped. Amazingly, this ice dam break happened not just one isolated time, but at least two and maybe as many as 100 times. The Purcell Trench refilling with ice, backing up the river, and then draining as if a giant had pulled a stopper out of a bathtub. The impact of the discovery of Glacial Lake Missoula's repeated and rapid flooding has changed the way scientists like J. Harlan Bretz, up to current researchers today, view epic events around the world. These monumental events happened so long ago. How can we know about these huge floods? Even though Glacial Lake Missoula is gone, there are clues that the curious geological detectives have followed in the last 100 years to piece together the puzzle of this ancient lake bed and the events shaping our landscape.
Follow the clues yourself and find more evidence of this amazing phenomenon in your own backyard. As you explore, post your photos on Instagram with hashtag Montana Natural History Center. Let's get started.
It's afternoon on a clear March day in Missoula. Standing on the University of Montana campus, you glance up at nearby Mount Sentinel and notice the uniform horizontal lines. The lines are echoes of the ancient Glacial Lake Missoula beach. They are Strand Lines, or shorelines.
They are our iconic feature. I mean, most people, I guess you have to maybe be a curious sort, but go, what are these lines doing on the hill? And might seek the story to understand it. The term strand line is kind of all-inclusive. It is simply meaning where the water came in contact with the mountainside. They're exactly parallel along the mountain front. They do not cross. They are always the same. And only a body of water could do that to a mountain. And they look like beaches. That's what they were. They were multiple beaches up and down the mountain. They were the highest on the mountain at the deepest part of the lake. So in Missoula, the lake was 1,000 feet deep. Probably drained and filled 40 to 100 times, but it didn't always fill back to the same level. As time went on, the lake level dropped. So that's why you see multiple lake levels. At the time Glacial Lake Missoula was here, it was quite desolate. Ice and ice water and icebergs and probably some hellacious storms. You can stand in the middle of the oval at the university, you can stand Camas Park, you can stand where we are now and look at the lake lines on the hill. I couldn't help but see them every time I looked at Jumbo and Sentinel and all the mountains around Missoula.
Engraved stone markers placed by the Glacial Lake Missoula chapter of the Ice Age Floods Institute show the high water marks at 4,200 feet on Mount Sentinel, Mount Jumbo, and Lake Como in the Bitterroot.
Become a geological detective. If you find a strand line, take a selfie with it and post it on Instagram with hashtag Montana Natural History Center.
Traveling the back roads west of Missoula, you encounter a spectacular landscape with dramatic mountain views framing open plains along Highway 200 from Dixon to Heron. The sight of undulating 30-foot giant ripples frozen in time at Camas Prairie Basin is eerie and striking. How did they form, and what story do they tell about the massive outburst floods of Glacial Lake Missoula? The Camas Prairie ripples were a key piece of evidence advancing the theory of the rapid draining of the ancient lake.
Ripples are a great thing and a great visual to think about. So we've all been down to the river or down to the beach and seen ripples forming by the water. And usually the ripples we see forming on the beach, they're in shallow water And these ripples are about an inch from one crest to the next. I've actually got some ripples here recorded in a rock. And you can see the difference from one crest to the next is about an inch. And this is a very natural process. It's due to the transport of sediment by the water moving over it. One of the real keys to breaking open the Lake Missoula story was when we realized that there were some ripples up in Camas, Prairie, just north of Missoula. But these were ripples where the distance between one crest to the next is now about 100 meters, or about a football field. And the height difference is about 3 meters, or about 10 feet. And we realized that these were ripples. They had to have been formed by water, but the scale of that water movement was nothing like what we are used to seeing. Must have been a huge flood, moving massive amounts of water and making ripples at a scale 100 times larger than we're used to seeing. The best place, honestly, to see the ripples is on Google Earth and to fly over Camas Prairie. They're just gonna pop. You're gonna see them. They're gonna look just like ripples you've seen anywhere else until you realize that it's a valley that you're looking at and not a small pond. You can drive there thinking this is the place that broke the Lake Missoula story open.
Head out to Camas Prairie to investigate the giant ripples that can be seen from space. Strain to hear the roar of the violent, ancient waters heaving gravel into undulating waves on the lake bottom. The ripples are now covered by quiet grasslands and vivid blue camas flowers in ancient still life.
Snap a photo and post it on the Montana Natural History Center website. #GLM Giant Ripples.
Patterns of light and dark of horizontally layered soil decorate sections of I-90 west of Missoula at 9 Mile. This geological artwork describes the rhythm of the ancient lake bed, the comings and goings that compressed the dark mud and light-colored silt into the lines and pages of the Glacial Lake story. Have the Rhythmites revealed the entire story? The answer is still being debated.
A rhythmite really means a sequence in the rocks that repeats itself over and over again. So what happens is in a rhythmite is we have a period of time where the water's going very fast and it carries big material or bigger material. And then we have a period where the water slows down and it drops smaller and smaller material. And in a rhythmite, this pattern repeats itself over and over again. It's rhythmic, so that's where the name rhythmite comes from. So Lake Missoula had several different rhythmites. The first one that we see in Missoula and the surrounding areas are the varves. And these are very common in glacial lakes. So in the summer, when the glaciers are actively melting, you have meltwater, it's carrying a bunch of rocks that are ground up by the glaciers into rock flour. And that rock flour is flowing out into the lake and it's getting deposited on the bottom of the lake. And it makes this big, thick, white deposit, the rock flour. And then the winter comes, it locks up the ice, the supply of the rock flour is cut off, and over the winter we deposit much less material. It makes a dark band, and then the next summer the process repeats itself. Those rhythmites are how we're trying to back out just how many times the lake actually filled and flooded. When we first put out the story of Lake Missoula, we thought it was one time. Then J. Harlan Bretz wrote a paper not too much longer where he said it filled and drained 3 or 4 times. When I was going to undergraduate school, we thought it filled and drained about 20 times. The current thought is that it could be anywhere between 20 and 100 times. As time goes on, we find evidence of more and more floods. I think the most important thing about a rhythmite is that it is recording individual events. It can be thought of much like a tree ring. It records an event that is repeatable, whether that's seasonal changes in a lake or repeated flooding and draining of the lake. As I learned more and more, I learned to understand that there were all kinds of rhythmites in nature recording these episodic flooding and receding type sequences. So I learned to interpret these repeatable sequences, think about history, think about how long Earth processes go on, It really just brings out how much history a rock can contain.
Post your thoughts and photos on Instagram with hashtag Montana Natural History Center.
Between Missoula and Sandpoint, the Clark Fork River squeezes through the rugged vertical-walled canyons. Anywhere canyon walls close in, the rushing river increased speed. Imagine the canyon narrows, or gorges, as a giant hose nozzle formed by cliffs, spewing 500 cubic miles of water, 60 times the flow of the Amazon River, along with rocks, debris, and silt through the gap. The sheer force of the flood scoured the vertical rock faces, leaving grooves in the bedrock 340 to 400 feet above the river. The sheer power of the event at Eddie Narrows, for example, is mind-boggling. Boulders shot through the gorge without bouncing off the river bottom at the top of the cliff face, just like cannonballs from a cannon. What must it have been like? The evidence left behind helps describe it.
Eddie Narrows is where all 5 arms of Lake Missoula finally came together, and all the water had to flow through this point. This makes it the best place to measure the flow rate and the speed of the water. At the flow rate of Eddie Narrows, the lake could empty in about a little over 2 days, and it determined the character of much of the rest of the flood, how big the other temporary lakes were. So it is really an important item to be aware of in the flood.
Narrows are basically anywhere where you have a stream channel, and that channel gets forced into a smaller area. And a great analog to this is we've all taken a garden hose, and when you don't have your thumb over it, the water's pouring out really slowly. And then when we put our thumb over the garden hose, that water sprays out very fast. That's because you're forcing the same amount of water through a much smaller area. And so a narrows is exactly that in a stream channel. We've taken a large amount of water and we've forced it into a small area, and it becomes a bit like a jet nozzle. And that water's forced to move very, very fast in order to move the same amount of water through this small constriction. And so when we have narrows, that's where the whitewater is. When we talk about narrows of Glacial Lake Missoula, then we're talking about narrows at a whole nother scale. When the lake flooded, the river was about 2 kilometers wide, or 2,000 meters wide. That's a little over a mile wide. So you've got to really just expand everything you know and think that you've observed in a river at 100 meters, you got to multiply it by about 100. So it gets about 100 times wider and about 100 times deeper. But we're still in a narrows, so we're going to have rapids, we're going to have waves, we're going to get a lot of the same things we see in rivers today, but they're just much, much bigger. Almost all the roads in western Montana follow the river course and would have followed a natural drainage pattern of Glacial Lake Missoula. Anywhere where you see the sides or the mountains close in on the freeway, that would have been a narrows anywhere around Missoula. Right now, you enter Albertan Gorge, which is a modern day narrows. Albertan Gorge, the walls of the river close in, and where that happens, we increase the speed and depth of the river, and we get these big rapids. And that's where people go to play in the river and get in whitewater today.
Curiosity and imagination help drive the scientists to interpret the ancient events and understand the present-day world a little better. If you're curious, explore Eddie Narrows or the Albertan Gorge to see firsthand the power of the Ice Age flood. Take a selfie and post it on Instagram with hashtag Montana Natural History Center.
You may have noticed lonely boulders littering fields, housing developments, and even the University of Montana campus. These alien objects, some as big as a car, don't match their surroundings. Orphaned rocks called erratics tumbled in the torrent of floodwaters or carried on ice rafts caused by the release of the ice dam have been adopted by geologists as clues to ancient cataclysmic events.
An erratic is a piece of rock that does not belong where you find it. Anytime you see a large erratic or a large rock that is just sitting out in the middle of the valley on the lake sediments, that's almost certainly an erratic. Usually they are transported by ice or on ice being pushed by the glaciers. Most of our erratics are of another kind, and those are the kind that are on icebergs or in icebergs. And the iceberg calves into the lake and drifts around until the iceberg either melts in the lake water itself, in which it's not only an erratic, but it's also an erratic dropstone. Or we burst the dam, all the water drains out, and we leave the iceberg stranded and it melts in the sun. That's the most common kind of large erratic that we have. Right at the corrals at the Buffalo Range, there is a house-size erratic framed by wonderful Strand Lines. One of the big ways to get big erratics is to have a rock slide land on the glacier. Then all of those rocks, that entire rock slide, will get incorporated into the ice and the icebergs, and they haven't been rounded at all. They're as rough as they were when they were in a landslide. Then the iceberg will take them somewhere and drop them, and they're not rounded at all. We have all kinds of erratics, and you have to really be thinking.
An erratic scavenger hunt is an entertaining way to explore the Glacial Lake Missoula activity. Find a lone boulder, snap a photo, and then try to determine where it came from. How far away is a rock of similar composition? Montana Natural History Center is interested in what you can find in and around the Missoula Valley. Post it on Instagram with hashtag Montana Natural History Center.
Megadunes, colks, and scablands, oh my! Knowing a bit of these geologic events as you travel the byways of western Montana helps you spy other clues left among the mountain valleys. As the river swirled through the narrow canyons, the velocity of the floodwaters increased. Sediment, gravel, and rock tumbled in the latte-colored whitewater. At Tarkio, the river course snaked through the canyon and slowed just long enough to drop gravel in a giant dune 500 feet above today's riverbed. The rounded rocks are the size of baseballs and footballs. This megadune is the biggest pile of gravel deposited by the flood. Megadunes and gulch fills are reminiscent of gravel bars among many western Montana rivers. Rocky holes and circular ponds certainly look out of place. What caused these? Imagine a water vortex, a spinning, abrasive tornado, more powerful than any drill bit augering basins out of bedrock. These are colks, made by hydraulic whirlpools and filled with debris as the floodwaters rushed west toward the ocean. Water moving at 65 miles an hour, almost freeway speed, sped down the path of the Clark Fork River, leaving behind a wounded landscape called scablands. Small areas of scabland can be viewed along the banks of today's river in various places.
To define megadunes, you have to think of what are dunes. And dunes are in rivers. They're like ripples in a river that are usually on the order of, are like 10 inches high to a few feet high. But in these big floods, like in the draining of Glacial Lake Missoula, megadunes are 30 feet high, 100 feet high, and up to 400 feet high. So they're like what you see in a stream, but just on a much larger scale. So Glacial Lake Missoula was very deep when it was at its high stand, and it drained very rapidly by the failure of the ice dam. So the water was rushing through the canyons at very high speed, at such a high speed that it was picking up gravel and just carrying it along in the stream. The gravel wasn't bouncing along the bottom, it was being carried throughout the flood height. And then as it was snaking through the Clark Fork Canyon, there were places where the velocities went down a little bit and they started depositing these dune structures. Well, what you see on these dune structures is they're shallow on the upstream side and they're deep, they're more steep on the downstream side, and they're up as much as 500 feet above the river level. So the normal river didn't deposit these things. It must have been a deep flowing flood through the canyons that was over 1,000 feet deep. When I started working in the late 90s, and ever since then, I'm discovering more and more things to investigate that haven't been investigated previously.
Becoming a practiced geological observer promises delightful road trips. Once on the trail of clues echoing through the centuries, you will be surprised at where the tracks will take you. Snap a photo and post it on Instagram with hashtag Montana Natural History Center.
The story of Glacial Lake Missoula is echoed in the scoured scablands west of the Missoula region. The massive flood, ice rafts, gravel, and sediment continued its frantic course through Idaho's panhandle, the barren but beautiful channeled scablands of eastern Washington, and the gorge of the Columbia River and the Pacific. The devastation left behind has been compared to the surface of Mars. Mars rovers have crawled the scablands, simulating a Martian invasion.
When the dam broke, the water went downstream. That means it went through Idaho, into eastern Washington, spilled across much of Washington, and eventually funneled down the Columbia River Gorge. It slopped up in the Willamette Valley, beyond Corvallis, and then went out to the ocean downstream from Portland. And some of that water, we have good evidence that it went all the way up to Vancouver Island in the deep sea to 10,000 feet below sea surface. There's sediments offshore Vancouver, British Columbia, that we can tie back to rocks in Montana.
As you travel west, follow the Ice Age Flood Institute's geological trail. Snap some photos and post them on Instagram with hashtag Montana Natural History Center.
Curious geological sleuths like J. Harlan Bretz, Joseph Pardee, and David Alt have described our home landscape by following the clues left in the soil, cliffs, and riverbeds of western Montana. The case continues to be fleshed out by present-day detectives using increasingly sophisticated technological tools. The floodies of the Missoula chapter of the Ice Age Flood Institute have developed a driving map and educational information to help everyone understand the impact of the flood and the story of the land in the Missoula region. The driving route is part of the larger Ice Age Floods Geologic Trail. The trail is a network of routes connecting interpretive facilities about the path of the Great Flood and is the first of its kind in the U.S. From the first indigenous people living on the land to today's students and scientists, curious people have been asking questions, observing the phenomenon, and slowly filling in the story of how our landscape was formed and what we might learn about the future.
A lot of people have heard of carbon-14 dating, where you can date bones, you can date teeth, and you can date burned wood. Unfortunately, you don't find any of that in the Glacial Lake Missoula section. And so there's a new technique. You can date the last time quartz or feldspar was exposed to the sun. And so it builds up, changes in its structure by natural radiation from the sediment around it if you bury it. And then when you expose it to the sun, it luminesces ever so slightly. And so that's what I've been using to date both the silt beds of the glacial lake deposits and now dating gravels for when the gravels were buried.
Water is the most important thing at the surface of the earth that shapes the earth. So when we look at rocks, what we're really doing is looking at the history of the hydrology of that particular area. And so when we look for this evidence of Glacial Lake Missoula, what we're looking at is records of how the water at that time was shaping the landscape. And those records are left behind when the water left.
The story of Glacial Lake Missoula is not fully written yet. Be a part of the saga. Be curious, and be amazed by what is in your own backyard.
There are hundreds of phenomena still undiscovered out there. Find some, take a photo, get the GPS coordinates, and post it. #Montana Natural History Center.